All right, I believe you have received a two-page handout. The handout is about how we can differentiate calculation problems in this gas chapter. There are 5 different types of calculation problems, and I just hope by making this flowchart, it will help us to tell one type from the others. As usual, we record and list any complete information, and also we need to write down the desired unit and entity as we already practiced many times since we started the unit analysis. Speaking of complete information, I'd like to remind you that it includes number, unit, and entity. Most of the time we see entity as a substance, but in chapter 5, entity could be heat. Well, after we finished laying out complete information and desired unit and entity, the first question we need to ask ourselves is, do we see any multiple identities of a gas? Or the keywords like a gas mixture, partial pressure, or total pressure, any of these mentioned somehow in a question? If the answer is a yes, it is the gas law, particularly Dalton gas law problem. And there are 3 equations I would like to remind you, not just one for the P total. If the answer for that question is no, the next question we need to ask ourselves is, do we see the multiple conditions of a gas? Things like 2 different pressures, 2 different temperatures, so on and so forth. If the answer is yes, it would be the problem that we have to use combined gas equation. I would like to remind you that we include N1 and N2 in this equation. Some videos on the internet do not. I figure that it is under the assumption that N1 is equal to N2, which I really do not think that is always true. So please have those N1 and N2 involved in this equation. If the answer for different gas conditions is no, our next question we need to ask ourselves is, how about a different gas or different entity? If we find out that the answer is a yes, it would be the stoichiometric calculation problems, because it is typical for such calculation by providing information about the 1 or 2 entities, but the question asks for something different or different entity. So here I give you a very useful conversion factor that can easily convert moles to liters at STP, which is a standard temperature and pressure, without further calculation using PV equals to nRT. Well, what about no for different gas and entity? Then we need look for the words like effusion, diffuse, diffusion, diffuse, because those words gives us a clue about the question should be used the equation from Graham's law. Well, if the answer for those questions no, it is ideal gas law problem, which is PV equals to nRT. So as we can see, there are 5 different equations or set of equations. So we need to go one step at a time by asking ourselves some keywords question or the multiple identities, so that we can tell and we can determine just which equation or which procedure that we're going to have to use. Next page is about the general strategies, or how we're going to start once we identify the type of calculation problems in this gas chapter. For example, Dalton's gas law. I would like to emphasize it is the first equation, the most important one, which means we have to figure out the moles of each gas. There are several scenarios in the questions that we're probably going to see later. For example, if the mass percent is given, for each gas. So what we're going to do is assume 100 grams of sample. We convert the mass percent of each gas into the grams, and then we use moles. Okay, so have the molar mass as a tool to calculate. Another scenario is we can convert molecular ratio, quite rare, but I do see some of the questions like this. So convert the molecular ratio into molar ratio. As a matter of fact, the molecular ratio is molar ratio. Then we can obtain the moles of each gas with the assumption of 100 grams moles of gas mixture. Another type of calculation problem, which is quite common, involves the same masses of gas. So question does not give us the exact mass for each gas, just to say it's the same masses. If we see this type of question, we just simply assume 100 grams for each gas and then get the moles by converting grams into the moles. Our next step will be to calculate the N total. So once we have the N total, so we can use the second and third equation to figure out what the question wants. As for the combined gas equation, it is extremely important for us to sort and organize two sets of variables. Same variable, even from a different set, must have the same unit. Particularly for temperature, it has to be Kelvin. We cannot use Celsius. Celsius is not allowed in any calculation involving gas. Meanwhile, we need to find out some variables that could be held as constant before and after change. If those variables are not mentioned, we can assume such variables are unchanged. As for the gas stoichiometry, we have practiced so many questions before, so we just simply follow the procedures we have established before. But one more time, 1 mole of gas equal to 22.4 liters of gas at STP becomes quite handy when we try to convert moles to the gas or gas liters to the gas. As for Graham's law, I just want to remind you to pay attention just how those molar masses are arranged. Okay. If A is on the left, on the top, then A must be at the bottom on the right. And don't forget, it is a square root, not just simply the ratio of molar masses. As PV equals to nRT, all I want to remind you is sure that the units of pressure and volume must match to each other. That means if a volume is in the unit of liter, pressure must be in ATM as its unit. If the pressure is in SI units, say Pascal, volume must be in the unit of a cubic meter. Again, temperature must be in Kelvin, Celsius is not allowed, and N must be in moles. Sometimes we are given grams, so we can use molar mass to convert mass into moles. Okay, so this is the general strategy of these 5 different types of calculation problems. Now let's look at some of the questions.